Okay, so I just wanted to start and go through just a different way to understand how to do electron configurations by using the periodic table. This is actually my preferred way to do it, but I think once you've learned it using the diagonal method, this way is a lot easier to understand. So I teach them in this order, even though ultimately this is the preferred way to do your electron configuration. So what you can see here is the periodic table, and I have identified the four main blocks of the periodic table with different colors. So up here we have the S block, and the S block is everything under this number 1 up top. We call that group 1. And everything in group 2, everything under this 2. And so those two groups together are the S block. If we travel across the periodic table over here, this big, what I call the square block, even though it's not, but it looks more square, the taller block over here, this is the P block. The middle block is called the D block. And the lower removed block, the one that's beneath, that is the F block of the periodic table. And what you hopefully are noticing is that these letters, S, P, D, and F, are very similar to the orbital letters that are a part of the angular momentum quantum number. And those are the very same letters. And so the first thing that I want to show you is that when we are doing an orbital diagram or an electron configuration, we can know how the configuration is going to end, with what letter the configuration is going to end, by looking at what block the element is in. So this is a colored in version of that same periodic table. We are looking right now at oxygen, atomic number of 8, O, right here, and O is located in which block of the periodic table? The P block, correct. So if we were going to do the electron configuration for oxygen, the electron configuration, remember, has the exponents or the superscripts. We would start, as always, with 1s, and 1s is going to have 2 electrons in it. The next one is 2s with 2 electrons in it. And then finally, we're going to go to 2p, and that has 4 electrons in it. This is the electron configuration for oxygen, and I want to show you a few things about it. First, start with me over here in the H up here at hydrogen. This is the 1s block. And so we're going to just move left to right, top to bottom, like we're reading the periodic table. So as we cross the S block, we hit hydrogen and then helium, SS. Then we come down here, this is 2s, and we go across lithium and beryllium, 1, 2. And we get this 2 here that matches the 2 squares we have crossed on the periodic table. Once we've crossed the 2s block, we're now in the 2p block. And we go 1 boron, 2 carbon, 3 nitrogen, 4 oxygen, 4 spaces over, and we find ourselves at 2p4. This is a coordinate on the periodic table. It is 2 rows down in the p block, 4 columns over, 2p4, and we have found oxygen here. This is like the Rosetta Stone of the periodic table. This is going to make the periodic table make a lot more sense to you. So let's look at a different example of aluminum. And I can use the periodic table to predict how aluminum's electron configuration will end. I'm going to count down to the row that aluminum is in. 1, 2, 3 spaces down, aluminum. It is in the P block, in this blue colored P block. And aluminum is in my first column. So I know that aluminum's electron configuration is going to end as 3p1. So if I want to figure out the rest of aluminum's electron configuration, I just start using the Aufbau's principle at 1s2, and I'm going to fill my way up. 2s2, 2p6, 3s2, 3p1. And now, if I want to check, which you always should, I'm going to do 2 plus 2 plus 6 is 10, plus 2 plus 1 is 13 electrons. And if I go look at aluminum, I would find that its atomic number is 13. So I've done it. I have configured aluminum correctly. And so in this way, you can predict the last piece of each of your electron configurations. I want to take one more second to count up each of our blocks before we move on. The last step of using the periodic table makes everything clear for us, but can sometimes be a little bit difficult the first time we see it. So, but before we do that, let's count up. The s block, as I hope you guys remember, our s orbital can hold a maximum of 2 electrons. P6, D10, F14. You may have noticed these ones aren't on the periodic table. We're not going to jump into that right now. But if we go find the S block on the periodic table, you will find that the S block contains 2 columns. 1, 2, 2 groups. 1, 2, and also can hold a maximum of 2 electrons. If we go to the P block, we will find 1, 2, 3, 4, 5, 6, 6 columns with a maximum of 6 electrons. If we go to the D block, we see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 with a maximum of 10 electrons. And our F block, I was careful to color this correctly here. These two, 57 and 89, actually belong as part of the D block. But if we start here and we count across with 58, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, no surprise here, 14 electrons in our F block. And so as we find the location, the column of the element in the periodic table, that will tell us the last exponent number of that orbital in the electron configuration. The last step to this is how we get our principal energy levels. And as you hopefully recall, our principal energy levels overlap as we get higher, farther away from the nucleus. So what I have written here now is the order that the orbitals fill using the diagonal method. And what I want to show you is how we can get this exact same order by looking at the periodic table. So if I start at 1s, in my first row, 1s fills across the periodic table. When I go to 2s, 2s fills, and then as I keep moving left to right, 2p fills next. As I come around, 3s fills next, and 3p. So far I've done 1s, 2s, 2p, 3s, 3p. Now as I keep moving across, I go through 4s, and here's the tricky part. I step down in my principal energy level because this is where the overlap begins, and I get 3d followed by 4p. Every time we step down into the D block, we're going to step down in our principal energy level. So when I have 5s, I'll still step down 1, 4d, and I'll step back up 5p. In the 6th period down here, we get even slightly more complicated. 6s fills first, followed by 4f. 4f is down here. Remember that connects in here in the 6th period. 4f, followed by 5d, and finally 6p. And so what I'd like you to do is I'd like you to predict how is this going to go in period 7. We know it's going to start with 7s. What would come next? After the S block comes the F block, 5f, and finally 6d. So adding this to the periodic table, that I had already colored in for you, I have put the numbers of the principal energy level of that block, and you'll see I kind of inserted the 3 here. So this would go 4s, 3d, and then the 4's over here, 4p. And down here it would go 6s, and then we go 4f, and then 5d, and finally 6p. So you don't have to use it fully this way, but certainly this is a different way to organize your electron configurations to make it even easier. And we'll just do a couple electron configurations together with a little bit of predicting and then also writing out the electron configuration. We'll just try a couple right now. So we're going to look at the electron configuration for silver. Silver is Ag, and it has 47 electrons. We find it right here, and it is in the D block. So we know that silver is in the D block, that much we know. We know that it is in the D block. And so now let's think, when we end silver, it's going to be what D? 1D, 2D, 3D, 4D, 5D, or 6D? Which one is it going to be? It is going to be 4D, because it's in the 5th period. And remember, that means we're going to go 5s and then 4D. 4D. And the last thing I know is that silver, the exponent or the superscript, if we start counting here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4D, 9 is where silver is going to end. So now when I'm doing its electron configuration, I can move much quicker to get up to 47 electrons. I don't have to keep counting. I can just move forward up to 47 electrons. So let's go ahead and try that. So we're going to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, we are here now. So after 4s2 comes 3d10, followed by 4p6. I'm over here. Now I'm back to 5s2 and 4d9. And this is my electron configuration for silver. If I wanted to make sure that I had done this correctly, I would add up all of the exponents. I don't mind doing some adding. So these first ones, 2 plus 2 plus 6, there's 10. And 2 plus 2 plus 6, here's another 10. And D block by itself gives us 10. And then we have 8 plus 9 is 17. So we have 10 plus 10 plus 10 plus 17, or 47 electrons, which is good news, because that's how many I was looking for. Good job, you guys. You're doing great. We're going to do one more together. We are going to look at germanium. Germanium has an atomic number of 32, and it's located right here. In order to find the electron configuration for germanium, what we're going to do is we're going to know that it's going to end in which block? The P block. What will its principal energy level be? What number comes first? Let's see, let's count down. 1, 2, 3, 4. We're in the 4th row. And as for the superscript, let's count across. Here is 1, and that is 2. 4p2 is the predicted end for germanium. So let's try it. 1s2, 2s2, 2p6. Remember, I'm reading across. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we go to 3d10. That's a little new for us. And we end at 4p2. Beautiful. Excellent. Great work, you guys. More practice in class when we get back together.